Okay, it's time for discussion 3.2, Electron Configurations and Valence Electrons. All right, so in 3.1 we talked about energy levels. Now, energy levels are actually made up of smaller parts. It's kind of like a Russian doll. Russian doll has a largest doll, which you can open and take out a smaller doll, which you can open and take out a smaller doll. So energy levels are the same way. They're kind of made up of smaller parts that we can't see unless we look. So energy levels are made up of smaller bits called sublevels. And each sublevel is made up of a different number of orbitals. And an orbital is just a region of space where there's a high probability of finding an electron. So there's 4 sublevels, S, P, D, and F. An S sublevel is made up of 1 single orbital. A P sublevel is made up of 3, a D sublevel has 5 orbitals in it, and an F sublevel has 7. So orbitals kind of look like this. S orbitals are spherical in shape. That's maybe where the S came from. P orbitals kind of look like dumbbells or kind of like peanuts. Maybe that's where the name come from. And D orbitals look sort of like a diaper without the tab if you drew the outline, but I guess not really. So the orbitals are associated with a particular amount of energy. It all depends on which energy level they live in. The orbitals that are farther away from the nucleus will have a greater energy than the ones that are closer, just like energy levels. So the orbitals are kind of seen as like hotel rooms where the electrons around the nucleus actually live. Okay, so we can see when we look at the periodic table that the table is broken up into 4 distinct regions, and each region is labeled with the letter S, P, D, or F. So when we look at the periodic table, the period number will tell you the number of principal energy levels an element has. It'll also tell you which period a particular level, or which energy level, a particular electron lives in. The letters S, P, D, and F tell you which sublevel those electrons are in, and each box means 1 more electron. Every time you move from one box to the next box will have 1 more electron than the box before it. So when we look at the S sublevel, if we want to determine how many electrons an S sublevel can hold, we have to look at how many boxes wide it is. The 1s is 2 boxes wide, the 2s is 2 boxes wide, the 3s is 2 boxes wide, and so forth. Since each box means 1 electron, that means that an S sublevel can hold a maximum of 2 electrons. The P sublevel is 6 electrons wide, or 6 boxes wide, so that means each P sublevel can hold 6 electrons. A D sublevel can hold 10, and an F sublevel is 14 boxes wide, so it can hold 14 electrons. So there's a trend that we can see, and that trend is the number of electrons per orbital. We see that 1 orbital can hold 2 electrons. That means 3 orbitals can hold 6, 5 can hold 10, and so forth. So when we look at an electron configuration, it's going to be a combination of letters and numbers. So what do the numbers and letters mean? Well, the most stable, lowest energy arrangement is called the ground state electron configuration. And for hydrogen, the ground state electron configuration is 1s1. Well, we have 3 different parts here. We have the coefficient, the letter, and the superscript. The coefficient tells us which period number or which energy level those electrons are occupying. The lowercase letter, it could be S, P, D, or F, tells us which sublevel those electrons are in. And the superscript tells us how many electrons are in that particular sublevel. So if I look at nitrogen, its electron configuration is 1s2, 2s2, 2p3. Right? That means that 2 of nitrogen's electrons live in the 1s sublevel, 2 live in the 2s sublevel, and 3 live in the 2p sublevel. All right, so when we go through the next slides, please make sure you have a periodic table handy because we figure out electron configurations by following the periodic table. All right, so first we have hydrogen. Now when we do an electron configuration, all we're doing is counting boxes on the periodic table. And we're going to continue to count boxes until we get to the element that we're asked for the configuration for. Right? Now when we count the boxes in the electron configuration, we have to note which energy level those boxes are in, which period, which sublevel those electrons are in, S, P, D, or F, and how many electrons are in that sublevel, or how many boxes we had to count as we were passing through. So for hydrogen, hydrogen has an atomic number of 1. It's the simplest element. That means its 1 electron lives in period 1 of the periodic table, in the S block of the table, in the first spot. Next, let's do calcium. Calcium has an atomic number of 20. So when we figure out the electron configuration for calcium, we're going to start at the beginning of the table and count each box until we get to calcium. So when I first start counting, I'm in period 1. And I'm in the S block of the table. And I have to count both of those boxes before I get to calcium, so the first factor is 1s2. After helium, element number 2, we come down to lithium, element number 3. Now we're counting boxes that are in period 2. They're also in the S block, and we're going to count both boxes, so the next factor in the electron configuration is 2s2. After beryllium, we go from element 4 to element 5, boron, which means we have left the 2s and now we're entering the 2p. Now, we have to count all the boxes until we get to calcium, so I'm going to count all 6 boxes in the 2p, which means the next factor is 2p6. After 2p, we come from element 10 to element 11, so now we're in the 3s. We're going to count both of those boxes, so the next factor is 3s2. After the 3s comes the 3p. Again, we're going to keep counting until we get to calcium, so we're going to count all those boxes. So we're going to count, so the next factor, is 3p6. After the 3p comes the 4s. Calcium is in the second spot in the 4s, so the electron configuration ends at 4s2. Now that may seem complicated, but all you have to do is follow the periodic table. I guarantee eventually everybody will get this if you practice. Furthermore, calcium is the biggest element that you have to write electron configurations for in Chem 1. That means if you can write the electron configuration for calcium, you can write all the electron configurations that you're required to write. And you'll see as we fill in the rest of these how each one is so similar to each other, it just has a different ending point. So next comes carbon. Carbon has an atomic number of 6, so we only have to count until we get to carbon. So again, we're going to start at the beginning of the table, and in the beginning of the table, we're in period 1, and we're going to count both of those boxes. So the electron configuration will start with 1s2. After the 1s, just like up here, comes the 2s, and we're going to count both of those boxes. So the next factor is 2s2. Now we enter the 2p, and carbon is in the 2p section of the table. Right? Now to get to carbon, I have to count 2 boxes in the 2p, so the configuration will end at 2p2. What I want to do now is have you pause the video and try these next 3 on your own. All right, so phosphorus has an atomic number of 15, so we're going to keep going until we get to phosphorus. So it starts with 1s2, then 2s2, 2p6, 3s2, and finally for phosphorus we stop at 3p3. For aluminum, aluminum has 13 electrons, which means it's going to have 2 fewer electrons than phosphorus. So when we start, it's 1s2, then 2s2, then 2p6, then 3s2, then 3p1. The only difference between phosphorus and aluminum is phosphorus resides in period 3 in the p block in the 3rd spot, and aluminum is in the p block in period 3 in the 1st spot. Finally, oxygen has an atomic number of 8. Oxygen's electron configuration will end at 2p4. So we're going to have 1s2, 2s2, 2p4, and that is oxygen's electron configuration. Now I just want to note that when you take all the superscripts in any electron configuration and add them up, they should add up to the atomic number. So we see here for oxygen, 2 plus 2 plus 4 is 8. 2 plus 2 plus 6 plus 2 plus 1 is 13, and so forth. So orbital diagrams. Orbital diagrams are just a way for us to show electron configurations in a visual way. So when we do this, we're going to indicate each orbital with a box or a line. I actually prefer lines because it's less work. And each line counts as a single orbital. So let's look at sodium. The electron configuration for sodium is 1s2, 2s2, 2p6, 3s1. Okay, so if I'm going to turn this into an orbital diagram, I'm going to need a line for each orbital in this electron configuration. Now we know that an s sublevel is only made up of one orbital, so I'll draw one line for the 1s. After the 1s comes the 2s, which also gets one line because it's an s. After the 2s comes the 2p. There's 3 orbitals in a 2p sublevel, one in the x-plane, one in the y-plane, one in the z-plane, so it's px, py, and pz. After the 2p comes the 3s, and again, there's one orbital in an s sublevel, so the 3s has one line. Now, electrons in each orbital are represented by up and down arrows. Each arrow counts as one electron. So for sodium orbital notation, there's 2 electrons in the 1s. Oh, hold on a second. So we put two arrows, one up, one down, in the 1s. We have 2 electrons in the 2s, 6 in the 2p, and 1 in the 3s. So when we're filling in orbital diagrams, there are 3 rules that we have to follow. The first is the Aufbau Principle. Now the Aufbau Principle says that electrons will occupy the lowest energy levels possible. And we call that the lazy tenant rule, right? Because if you had a building that was empty and it did not have an elevator in it, the first apartments to go will probably be the ones on the lowest floors. That way you don't have to walk up all those flights every time you come home. So we see here a variety of electron configurations. You can see that they all have electrons filling the lowest energy orbitals first before any higher energy orbitals can be full. The Pauli exclusion principle says that orbitals can only hold 2 electrons, which we already know, and both electrons will have opposite spin. Now we show the opposite spin by just putting one arrow up and one arrow down. The direction of the arrow represents the spin of the electrons. Finally, Hund's rule says that one electron must fill each orbital in a given sublevel before any pairing takes place. And we call that the kids on the bus rule. Now, when I was a kid, my bus driver would only let kids start to pair up in seats once all the seats had one kid in them. Now they did this because they know that your friends probably live in the same neighborhood as you, and if your friends are together, they're going to cause more havoc than if you're sitting next to a stranger. So the same thing is true. Within a given sublevel, we cannot start pairing up electrons until we put one electron in each box. So let's do some practice. So I'm going to go through this slide as if you already know the electron configurations. So for calcium, we know calcium will end at 4s2. So I'll start by filling in the last 2 electrons in the electron configuration. Because of the Aufbau principle, we know that the 4s will not have any electrons in it until all the other orbitals are filled. So once you fill in the 4s, boom, you can just put in all the rest of the arrows. Hydrogen is 1, so its electron configuration is 1s1, so we show that 1 electron in the 1s sublevel. Carbon has an electron configuration, atomic number of 6. So that means that carbon, because it ends at 2p2, is going to have 2 electrons in the 2p. This is where we have to follow Hund's rule. When we fill in those electrons, I'm going to put 1 in the 2px and then 1 in the 2pz. I'm not going to put any other electrons in any other orbitals in that 2p sublevel until all 3 have an electron in them. Since carbon only has 2 electrons in the 2p is full for carbon, and that means everything that comes before it is also full. Take a moment and try these 3 all on your own. Okay, so phosphorus has 15 electrons. Phosphorus ends at 3p3. That means we're going to have 1, 2, 3 electrons in the 3p. Whoops. Found an error. Let me just copy, paste. Sorry, I don't like to adjust these while I'm making them, but sometimes you got to do what you got to do. Oh, where's that last electron? Oh, sorry. There should be 1 more electron in the 3p. All right, anyways, aluminum has an atomic number of 13. Aluminum ends at 3p1, so 1 electron goes in the 3p, and all the orbitals before it are full. Finally, oxygen has 8 electrons, and it ends at 2p4. That means we need 4 electrons in the 2p. When you fill them in, do them one at a time. So 1, 2, 3, 4, and then everything else is filled in. There you are. There's that last crooked electron in the 3p. Okay, so shorthand electron configurations. So it can be a little bit cumbersome to write out long electron configurations. So to shorten it, we use the previous noble gas in brackets to represent the configuration up to that point. So let me give you an example. For potassium, if we wanted to do the electron configuration, we could write out 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. But we know the electron configuration of the noble gas that comes before it, argon. When we take the symbol for argon and put it in brackets, we're saying that what's in brackets is the electron configuration of argon. After argon, all we have to add is that one electron in the 4s, and that is the shorthand notation for potassium. For calcium, it has a similar electron configuration to potassium, just one more electron, so its shorthand would be argon 4s2. Now, I have argon here because what a lot of kids like to do is just put argon in brackets and call that the shorthand configuration. But to get the shorthand configuration, we always use the previous noble gas to represent the configuration up to that point. So for argon, the previous noble gas is neon, and the rest of the configuration is 3s2, 3p6. Finally, for boron, the previous noble gas is helium. After helium, we have 2s2 and 2p1. Just beware, I'm going to ask you specifically for either shorthand or full electron configurations. Give me the one that I asked for, please. All right, so valence electrons. So valence electrons are electrons that occupy the outermost energy level of an atom. And the significance of that is that the number of valence electrons will actually determine the chemical properties of those elements. And the octet rule says that atoms will either gain or lose electrons in order to become stable. And we know that the most stable elements on the periodic table are noble gases. So everybody wants to have the same number of valence electrons as a noble gas. So counting valence electrons is absolutely key in this course. It's one of the most important aspects. So really focus on learning this because it'll make so many things down the road easier. So when I look at helium, I have to look at the electron configuration. Remember that the coefficient number is the period number, which represents the number of energy levels. The highest numbered coefficient will tell you what the highest energy level is. For helium, the highest energy level is number 1, and there's 2 electrons in it, so it has 2 valence electrons. For lithium, the highest energy level is the second energy level, and there's 1 electron in it, so lithium has 1 valence electron. Not coincidentally, it's also found in group 1. For beryllium, the outermost energy level is the second energy level, and there's 2 electrons in that energy level, so beryllium has 2 valence electrons, and it is found in group 2. Now, when we're looking at boron, we have to be careful. Kids always have a tendency to just say that there's 1 valence electron there, but in actuality, there's more than that, because the second energy level is made up of an s orbital, or an s sublevel, excuse me, and a p sublevel. So when you add all those up, boron will have a total of 3 valence electrons, and boron is found in group 13. Finally, for sodium, the highest energy level is the third energy level. There's 1 electron in it, so sodium has 1 valence electron, and sodium is also found in group 1. All right, so valence electrons and dot structures. Dot structures just show how the valence electrons are distributed, right? So to do a dot structure, all we do is put the number of valence electrons, the valence electrons around an atom symbol to show how many it's got and where they are. So let's first look at lithium. Lithium is in group 1. That means it has 1 valence electron. And so its dot structure is a symbol of lithium with a dot. Beryllium is in group 2, which means it has 2 valence electrons. And so its dot structure will be the symbol for beryllium with 2 dots. Notice I didn't put the 2 dots together. I put 1 dot here and 1 dot there on the other side. That becomes important later. So carbon is in group 14, and it has 4 valence electrons. So when I do its dot structure, I write the symbol for carbon and put 4 dots around it, 1 at a time. We're basically just following Hund's rule here. We're not pairing up any electrons until all the little spaces around the atom have 1. Finally, for oxygen, it's in group 16, so I bet you can guess it has 6 valence electrons. So when we do its dot structure, we write the symbol for oxygen, we add 1 at a time, 1, 2, 3, 4. Once you have 4, you can begin pairing them up, 5, 6. All right, so finally, trends in valence electron. You probably figured by now that the group number will correspond to the number of valence electrons. All the elements in the same group on a periodic table will have the same number of valence electrons. And that is why they have similar properties, because the valence electrons and the electron configuration for an element will determine how it behaves chemically. So all the elements in period 1 have 1 valence electron. All the elements in period 2 have 2 valence electrons. Now for groups 13 through 18, just drop the 1, and that will tell you how many valence electrons. So 3 and 13, 4 and 14, 5 and 15, etc. All right, and that does it for discussion 3.2. Thank you so much, as always, for watching. Bring any questions you have to class. Practice, 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 and I'll see you soon.